Hello, lovely humans. Jen Foxbot here. I'm going to do a TLDR version of Mama Llama's great question. Hey, Mama Llama. It's Pocket Llama right now. Great question about integral calculus because I know y'all are busy and you're like, you made a 20-minute video. I know. I love this stuff. So I like to talk about it a lot. So here's the TLDR beginner-friendly version of what is integral calculus? What is the hullabaloo about with calculus? Why do I have to know it for all the things? Well, integral calculus is super useful because it allows you to find areas and volumes of really funky shapes without having to do measuring by hand. Super helpful. So to illustrate this, literally and metaphorically, let's say that we move into a new place and it has a yard that's really, really funky shaped, and it is given by this curve on one side, and then our fence along the horizontal is like this, and then we have another fence line over here. And we want to get a furry friend, but we're like, do I have space for a large dog? Or is my yard more suitable for a teeny tiny little bunny? We need to know how big our yard is to figure out what furry friend will fit appropriately in that yard. But we go out and we're like, I don't want to measure that by hand. If you were really motivated and you didn't want to do integral calculus, it would take a lot longer, I promise. But you could get a bunch of rocks, lay them out all over the area, gather them back up, put them in a shape that was a little easier to measure, like a rectangle or something like that, and then you could calculate the area based on that. That's a lot of work though, and I like to be lazy, yes. So that's where integral calculus comes in. And what we do is we take the integral of our function f of x with respect to the variable dx, and since we are doing it over a defined area, that's called a definite integral. So we are taking the integral from 0 to 2 meters of our function f of x. So we plug in x squared for f of x with respect to dx. And this is where I'm going to hand wavy say these are the rules of integral calculus, just like addition, subtraction, multiplication, division. We have to learn the rules of how the symbols work. And once we learn the rules, no problem. And you can look them up. That's the secret. Well, not so secret. That is a good recommendation. So we do the integral of x squared, which comes out to be 1/3 x cubed from 0 to 2 meters. And when we plug that in, we get 8 over 3 meters squared. And I'm doing a little bit of hand wavy stuff here, but basically there is a unit that we would kind of bring in with this x squared that is going to actually be like 1 over meters, because the vertical axis is in meters. So f of x is in meters. If you're like, what just happened? Don't worry about it. It's just me trying to be consistent with units and area, which is meters squared. We can get into it more in the comments if you're curious. Okay, so we are able to calculate the area under this curve very quickly with integral calculus. But wait, what is going on? What is this dx shenanigans? Great question, audience. So dx is an infinitesimal, which means it is infinitely small. And it was invented because this is basically the integral sign, this like funky, delightful S up here, which I just drew really confusing because it kind of looks like the way I draw F. But it is kind of an elongated S, and that means it is a sum using the infinitesimal dx. If we were to draw it, which is super helpful, what we are really doing is we are adding up tiny little rectangles under the curve until we get all the way here, and then we get this larger rectangle. The width of these is dx. So each of these little rectangles has a width dx and a height of f of x at that given point, I guess. So you would calculate what f of x is at this point, because dx is so small, you can say, okay, well, it's just at a point, and then you would sum it up over all of those different points. And the width of the rectangles is going to determine how many points you want to take. So if you only take a couple of points, you're going to have a rectangle that's pretty large, and it's going to be a very rough approximation. So the smaller that you make those rectangles, the more points that you calculate f of x at, then the more accurate you can be. But calculus, integral calculus, lets us just say we are going to take the continuous sum so that we actually get the curve. So basically we are taking an infinite number of points between 0 and 2 and summing that up to get this area. Pretty cool, right? Yeah. If you're like, wait, what is an infinitesimal? And I just blew your brain a little bit. They are super cool, and I have a whole video on them. Would highly, highly recommend. They are such a cool concept in mathematics and a very, very useful tool. Okay, so how much time are we at? Oh, 6 minutes. I was like under 5. Okay, almost made it. Well, I hope that that is helpful. It's a lot to cover with integral calculus, but it's really, really useful. And also, you are totally capable of learning it because it is just a language, and it's all about understanding what the symbols mean and what you're doing. It's a tool. You can learn how to use the tool. So I hope that was a good TLDR, shorter than 20 minutes. Shorter than 20 minutes, okay. Please let me know if you have any questions about science, tech, engineering, or math. Thank you very much for joining me, and we'll see you next time. Bye.